Welcome back. In this video, we will continue to learn about organic chemistry by focusing on what are called geometric isomers. We'll also learn how to label them as being cis or trans geometric isomers. In a previous video, we discussed constitutional isomers as being molecules that have the same molecular formula, but a different arrangement of the atoms. Let's take a look at a different type of isomer. This will come up when we draw butene. As we have talked about before, but is the prefix that means that we have 4 carbons, and ene means that it's an alkene. So we could get one butene, where the carbon-carbon double bond is between the first and the second carbon. We could also get what's called 2-methylpropene. Essentially what we've done here is we've taken and moved one of the carbons right there. Okay? We could get trans-2-butene. Trans-2-butene, we've essentially put the double bond in between carbons 2 and 3. And then finally we have cis-2-butene. And here as well, we see that the double bond is between carbons 2 and 3. But these molecules are different from each other. You can see that the physical arrangement of those atoms is different. What causes this? What are these called? These are the geometric isomers. These are when we get pairs of molecules that differ only in the geometric arrangement of the groups around the double bond. So if we draw out these structures completely, we remember we have these hydrogen atoms on here. And what we can see is that in one case, these hydrogen atoms are across from each other with respect to that double bond, or they're on the same side as each other with respect to that double bond. So if you draw a line down that double bond, you can see that in one case, again, they're on opposite sides of that line, or they're on the same side of that line. And we will see shortly that that's one of the tests for geometric isomers. So here we have 3 constitutional isomers: 1-butene, 2-butene, and 2-methylpropene. But within 2-butene, we also have 2 geometric isomers. We have the trans version and we have the cis version. And these geometric isomers are chemically different from each other. They have their own unique properties in a similar way that constitutional isomers are different from each other. So as we saw earlier, one way to test for there being a geometric isomer is to find a molecule with a double bond and to draw a line through that double bond along that carbon-carbon double bond axis. And then what you do is you look at the relationship between the groups attached to each of those carbons. So if we were to label these carbon 1, actually let's stick with our notation: carbon 2, carbon 3, carbon 4, carbon 1, carbon 2, carbon 3, carbon 4. You can see that carbon 1 in both cases is attached to 3 hydrogens, and it's attached to carbon 2. Carbon 2 is attached to carbons 1 and 3, and 1 hydrogen in both cases. And we could repeat that process and see that indeed each carbon atom is attached to the same elements. Each hydrogen atom is attached to the same elements. But these are physically different molecules. And the reason for it is because the double bonds do not rotate around. They're stuck in a fixed position. And so the relationship between carbon 1 and carbon 4 is different in the 2 structures. Again, we can see in the trans configuration, draw that dotted line, that they're across from each other with respect to that double bond, whereas in the cis configuration, they're on the same side of that double bond. And there's a really simple way to determine whether or not a molecule has a geometric isomer. The first thing that you do is you identify the 2 carbons in the double bond. you look at the carbon on the left and you ask, are the groups attached to this carbon different from each other? So in this case, is whatever atom 1 and atom 2 are they different or are they the same? And then you ask for the other carbon, are the atoms 3 and 4 different or the same? If the answer to both of those questions is yes, then that molecule has a geometric isomer. So essentially what we need is that the atoms 1 and 2 must not be the same, and 3 and 4 must not be the same. But it's okay to get 1 and 3 equal, or 1 and 4, or even 2 and 3. It's just that the elements attached to these carbons must be different from each other. Okay? So here, 1 and 2 are different, 3 and 4 are different. So what we can do is if we take this molecule and we essentially rotate, we keep 2 of those elements the same, but we rotate these 2, we swap them, you can see that we get a different arrangement. The relationship between groups 2 and 4 was on the same side, so they were cis, but now they're opposite. They're trans to each other. All right, so here's a practice problem for you. I'd like for you to identify which of these molecules could have geometric isomers. Welcome back. So in order for a molecule to have a geometric isomer, we need to have carbon-carbon double bonds. Okay? And that then eliminates D and E. The next thing that we do is we look at the groups on either side of those carbon-carbon double bonds. We'll label them 1, 2, 3, and 4. And we ask, are groups 1 and 2 the same? Are groups 3 and 4 the same? Groups 1 and 2 must be different, as well as groups 3 and 4. So for molecule A, you can see that here we have 2 hydrogens. Well, those are the same, so this can't be a geometric isomer. What about in B? In B, we have here, we've got a carbon or a hydrogen and then a CH3 group. And here we have CH3 and CH3. So that can't have a geometric isomer because these 2 groups are the same. Now, what about here in C? We do have a carbon-carbon double bond. This is a hydrogen, that's a hydrogen, and then this group is a CH3, and this group is CH2, CH3. And so you can see that those groups are different from each other. Therefore, this one can have a geometric isomer. If we wanted to identify what its geometric isomer was, we would take and essentially rotate around that bond or swap the positions of any 2 of these groups. So you can see here what was this molecule. We've now taken the hydrogen and the CH3 group and we've swapped their locations. The CH3 is here and the hydrogen is there. And therefore, that's its geometric isomer. That's it for this video. Thanks for watching. Have a great day.